Are you a last-minute JAMB UTME candidate? Don't panic, I can help you. Do you need this lesson notes as simplified and short as it is, covering the whole JAMB UTME syllabus 2026, leaving no single stone unturned? You can get this file, okay? You can get this file. All you need to do, send me a DM. Do you want the sharp plan for last-minute preparation that UTME candidates have been using for over 4 years now? All you have to do, send me a DM, drop me a DM through my phone number, go to my profile. On my bio, you are going to see my phone number there. Add up and send me a message, and I will supply you all this material for you to prepare for your JAMB UTME. Trust me, the outcome is going to be what? Flamboyant. The outcome is going to be worthwhile. It's going to be worthwhile. I can still work on you within this short period of time. JAMB 2026 candidates, don't fail for any reason. Even though say now 2 weeks you dey prepare, I can still make a difference in your JAMB UTME 2026 score. Welcome to the continuation of our lecture on physics in preparation for JAMB UTME 2026. We have gone so far. We are almost done. So I'm telling you, congratulations in advance. So before we begin, please get your pen and your notebook, your physics notebook, to jot down whatever you understand of this lecture, because we are going higher and higher and higher and higher. Today, we are looking at the topic induction. What do you understand by induction? Induction is bringing about. So anytime you hear induction, just remember bringing about, cause it, to cause something, to bring about, okay, to induce, all right? That's induction. And the law, Faraday's law and Lenz law, these two laws in electricity explains induction. Both Faraday and Lenz are the core contributors to induction in physics. So let's look at Faraday's law first of all. So the Faraday's law of induction states that the EMF is induced by the changing flux. What it says that the electromotive force is caused by the changing flux. Changing flux. You know what flux is now? Okay, that thing that makes you experience magnetic field, or that thing that makes magnetic field to be experienced. That's flux. All right. So that's flux. It's like a web. Okay, it's like spider web, okay, around the spider. So that is flux, all right? So in essence, what does this explain? EMF induces by changing flux. So EMF is induced by a changing flux. It means that magnitude in the system is directly proportional to the rate of change. So the rate of change of flux is directly proportional to the magnitude, all right? The rate of change of flux, or the rate of change of what? Electromotive force is directly proportional to magnitude, all right? So electromotive force is controlled by what? It's controlled by the magnitude, which is the magnitude. When you say magnitude, you are talking about the flux. Okay, the flux, movement, that which brings about movement, the magnitude. All right. Now let's look at Lenz law. All right, it's very easy. He said the induced current flow in such a direction opposes the change producing it. The induced current flow in a direction opposes the change producing it. It's a law that conserves energy. I can't explain Lenz law more simpler than this. It's the induced current flow. Lenz law states that induced current flow in a direction opposes the change producing it. So that thing where they produce the induced current flow in that particular direction opposes that change producing it. That's the change in flux. Remember, change in flux equals what? EMF, okay, or induced EMF. All right, don't forget that. Now let's look at the factors affecting induced current. All right, the first one is area. Area affects induced current. The second one is B. What is B? You know, so what is B? Do you know what B is? You sabi waiting B. So why speed also affects what? Induced current. Okay, and the turns. Now, let's look at the types of generators. First of all, do you know what a generator is? At least you use all those ones for house now. So a generator is that which converts energy from one form to another. What form of energy does it convert? Depending on the kind of generator. If it's a generator that uses potential energy to run, for example, like the gasoline generator we use here in Nigeria, all right? So the gasoline generator uses potential energy, which is in fuel, okay? It converts the potential energy to what? To kinetic energy or to mechanical energy. And the mechanical energy is further converted to what? To electrical energy. All right, so heat is given off. So heat energy. So it's about how many conversion. The functioning, the mechanics of the generator, gasoline generator, is how many conversion of energy is involved. You have 3 conversion of energy, from potential to heat, from heat to kinetic, from kinetic to what? To electrical. That's it. About 3. Okay, 3 conversion. All right. So we have 2 types of generators. All right. We have the AC generator, which is the alternating current generator. It produces alternating current. All right. Or you can see what's written here: alternating EMF, alternating electromotive force. It's a kind of force, or it's a kind of current or volts that changes. Okay, with direction. It changes with direction. It changes. It alters. Okay, that's why it's called alternating current. It changes on its own. Okay, that's why in an alternating current you can connect positive to negative and connect negative to positive. Nothing will happen. It's going to alternate it. It's going to change it and continue running. Nothing will happen. But if you try out for DC, direct current, it could just burn. You go connect positive and negative. Instead of connecting positive to positive, you went and connected positive to negative. You could just burn. But in alternating current, you are safe. All right, or alternating EMF. So the DC generator comprises of a commutator. So the commutator is something called a split ring. All right, it's called a split ring, and it's found in a what? In a DC generator. What does it do? It converts direct current to what? To alternating current. In fact, commutators are found in both the alternating EMF generator and the direct EMF generator, but it boils down to the type of commutator found in both. All right. So in the alternating current or the alternating EMF generator, you have a kind of commutator called the slip ring. Slip ring, that's the type of commutator you have there, slip ring, okay? And what does it do? The slip ring ensures that alternating current is given out as the output, all right? While in the direct EMF generator, you have a commutator called split ring, okay? And what does this split ring do? What is its function? Okay, its function is to ensure that the output of the direct current generator is direct current, okay, or direct EMF, okay? That's it. So let's look at transformers. Types. What are the types of transformer? We have majorly two types of transformer. The first is the step-up transformer and the step-down transformer. Both of them step up and step down voltage, respectively. The step-up transformer steps up voltage, while the step-down transformer steps down voltage. And the efficiency of transformers are usually very high. So what is the difference between the step-up transformer and the step-down transformer? I will tell you, I'll give you an overview, all right? In the transformer, there is something called the primary coil and the secondary coil. That's the primary turns of wire, majorly most of the time commonly copper wire turns. We have the primary coil and the secondary coil. In a step-up transformer, the secondary coil is more. You have more secondary turns, or you have more turns in the secondary coil as compared to the primary coil. But in a step-down transformer, you have more primary coil than the secondary coil. That's the turns in the primary coil is more than what you have in the secondary coil. So that's the key difference between a step-up and a step-down transformer. And another difference is that the step-up transformer is used to raise voltage, okay, to increase voltage, while the step-down transformer is used to bring down voltage. All right. So induction coil. What does induction coil do? Induction coil produces high voltage sparks. That's the function. JAMB says that we should look at the function of induction coil. So induction coil does what? Produces high voltage sparks. All right. Now we are looking at the type of transformer. We are going in depth on the types of transformers. All right. The first we have is, I already told you, we have step-up transformer. Step-up transformer does what? It increases voltage and decreases what? Current. You know that as voltage increases, current decreases. All right. So the step-up transformer increases voltage and decreases current, and it has what? More secondary coil, okay, or more turns in the secondary coil. And let's look at the step-down transformer. What does the step-down transformer do? It decreases voltage and increases current. Okay, it's what? It decreases voltage and increases current. Okay, remember, when voltage increases, current decreases. When current increases, voltage decreases. Voltage and current are inversely proportional. All right. Now let's look at the working principles of transformer. The transformers function under the Faraday laws of what? Electromagnetic induction. What is induction? Inducing through current. So that's the principle that transformer works under. Okay. And how does it function? Let's look at the breakdown. Okay. Alternating current is induced into the primary coil. That's, you put alternating current, AC, into the primary coil. And what happens as you do this? It leads to what? Changing in flux in coil. Remember the Faraday law of induction. Okay. Changing in flux is directly proportional, is equal to what? Magnitude. All right. It leads to what? Changing in what? Flux in the coil. And what does this lead to in turn? It leads to an induced voltage in the secondary coil. That's the voltage does what? There's an induced voltage in the secondary coil. So the voltage, whether the voltage is going to be high or low, is determined by the turns in the coil. That's what makes them step-up transformer or step-down transformer. The turns in the what? In the secondary coil. Is the turns in the secondary coil more than what you have in the primary coil? You already know the kind of transformer that is. Okay. Is the turns in the primary coil more than that in the secondary coil? You already know the kind of transformer that is. All right. So I've explained this and broken this down. I've simplified this. Now let's understand what is meant by the concept inductance. Okay. It's very easy. Inductance is the property of an inductor to oppose change in current by inducing an electromotive force, EMF. When an inductor opposes change according to Lenz Law. When an inductor does what? Opposes change in current by what? Inducing an electromotive force. So the inductor induces an electromotive force to what? To oppose change, okay, in the current. That's fluctuation of flux, okay? It opposes it, okay? It acts against it, okay? That's inductance, okay? The property of an inductor to oppose change, okay? To change what is going on in the current by inducing an electromotive force. There's an induced electromotive force. So in inductance, there's an induced electromotive force. But in Lenz Law, there is induced current. All right, induced current. All right, remember, electromotive force is measured in volts. So when we speak about electromotive force, we are talking about volts. This inductance depends on coil turns. The inductance does what? It depends on what? Coil turns. And not just only the coil turns, okay? It also depends in the core material. What material was used? Is it soft iron core? Is it hard iron core? What material was used? Is it copper wire? What kind of insulated wire was used? Okay, is it aluminum wire? And it's also dependent in the geometry. When you say geometry, at what angle was this particular coil turned? What was it wound in? At what angle was the coil wound in? At what dimension was it given? Okay, so the geometry also what? Affect inductance. So if you ask you factors that affect inductance, coil turns, core material, and what? Geometry, which is the dimension, the angles. All right, this angle determines the location of various components of the the inductor. All right, it determines the location. How are they located? How are they brought together? How were they integrated? That's what this geometry is all about. All right. So what is the SI unit of inductance? It's Henry. Henry, like that name, Henry. All right. So we have various connection of inductance, just like capacitor and resistance. So we have two connections of inductance. Okay. And just like resistance, okay, you have resistance in series and resistance in parallel. All right. So we have inductance in what? Series, okay, and inductance in what? Parallel. Okay. It's just the same as resistance. The same way you solve that of resistance is the same way you solve that of what? Inductance. All right. So total inductance is equal to what? L1 plus L2 plus L3. You just add. If it is connected in series, you just add everything together and get your total inductance. But if it's connected in parallel, 1 over total inductance is equal to 1 over L1 plus 1 over L2 plus 1 over L3 plus 1 and so on and so forth. Then instead of it to use that long cut LCM, that long Johnny LCM style, use my style. You times both to form numerator, then you plus both to form denominator, then you what? You divide. To get your what? Answer. Very easy. Sharp, sharp. Sharp, sharp. Within 15 seconds, you don't solve. Come on here. All right. So the energy of an inductor is what? How do we calculate the energy of an inductor? The energy of inductor is given by half of the inductor times the square of the current. Half of the inductor times the square of the current. So you can see what we have here. 1 over 2 inductor times I square, which is the square of the current. Remember. Voltage affects what? Inductance. What is the use of inductance? Where is it applied in? So inductance is applied in filters. All right, it's applied in filters, it's applied in motors, electric motors and generators, it's applied in transformers, it's applied in energy storage, energy storage system. Okay, so anything that involves induced current, all right, opposing change. You know that this opposition of change prevents energy loss or minimizes energy loss. This opposition of change minimizes energy loss. That's why where you have storage of energy, it works. Where you have transformer, where current is converted, requiring conversion, you use inductance. Inductance is applied in motors where you need conversion from maybe from electrical or induced current, electric, towards magnetism. Induction is needed. Have you heard of induction motor? Induction motor and induction generators. Now let's look at eddy current. I so much love this subtopic, eddy current. I too love eddy current. Eddy current. All right. What is eddy current? Eddy currents are loops of induced electric current that form inside a conductor when it is exposed to a charging magnetic field. Eddy currents are loops of induced currents that forms inside a what? A conductor when it is exposed to a changing magnetic field. So when you expose a conductor to a changing magnetic field, this is how you form alternator. Okay, you form alternator for generator. So when it's part of everything, so when you expose a conductor to a changing magnetic field, what happens? What happens? There is a loop of current induced. Okay, there's a loop of electric current induced. So how do we reduce the loss of eddy current? Because eddy current is very beneficial. Like I just told you. Eddy current is part of the principle at which your gen runs, your generator at home. The coil of your generator, the alternator, is part of the process, is part of the mechanism. So when you have a changing magnetic field around the conductor, that's the magnetic field you have in your alternator, there are loops of currents in the system or around the conductor. Okay, that loop of current, that's this eddy current that we are talking about. It helps in what is called electromagnetic induction of current through electromagnets. All right. Since eddy current is beneficial, how do we reduce the losses of eddy current? How do we reduce the losses of eddy current in a system, in an electrical system, in an electromagnetic system, in an induction system? How do we do that? First of all, the first thing to do is to use laminated cores. All the iron cores or metallic cores you have in the system, use a laminated one. Ensure that they are laminated. When you say you laminated, ensure that they are properly insulated. The second thing to do is use thin sections. Okay, use what? Thin sections. Ensure that the sections are thin. Those edges, ensure that they are thin. Okay, you know, it's section. You put this one on top, this one. You know the core now, the core of iron. You know how transformer be now. If you scatter, no, I don't mean big transformer like the ones that help to step down voltage in your streets. I don't mean that one. I mean small transformer where you see for inside charger, for inside stabilizer, all those kind of transformer. If you disassemble them, you are going to see the slices of the core, usually soft iron core, used to make them. Okay, so it's saying if you want to reduce eddy current, thin, ensure that the sections are thin. Okay. Then the third one is high resistivity or silicon steel to restrict current path. So use high resistivity or silicon steel to restrict current path. All right. So what are the uses of eddy currents? Okay, eddy currents are used in braking. Okay, in braking, such as in trains, roller coasters, it helps to do braking. All right. So eddy current is also used in induction heating, such as for cooking and metal hardening. All right. So eddy current is also used in what? Magnetic damping. Okay, such as in meters, meter and instruments. All right. So eddy current is also used in what? Testing/detection. All right. Metal flaws, use it to detect metal flaws and other detectors. All right. Now that we have understood Lenz's contribution to electricity, Faraday's contribution to electricity, induced current, induction and eddy current, let's now use some JAMB must repeat question to test how well we understood this lesson and also measure how prepared we are for the upcoming JAMB UTME 2026. JAMB must repeat question 207. Faraday's law states EMF is proportional to what? A. Flux. B. Rate of change of flux. C. Current. D. Resistance. What's the answer? Drop the answer in the comment section. Question 208. Lenz law illustrates A. Energy creation. B. Energy conservation. C. Heat loss. D. Current flow. What's the answer? Drop the answer in the comment section, my scholar. Question 209. Transformer works on what? A. Self-induction. B. Mutual induction. C. Eddy currents. D. Resistance. What's the answer? Drop the answer in the comment section, my scholar. Question 210. Inductance units is what? What's the unit of inductance? Is it farad? Is it Henry? Is it ohms? Is it volt? What's the answer? Drop the answer in the comment section, my scholar. Question 211. Eddy current losses are reduced by what? A. Solid cores. B. Laminated cores. C. High voltage. D. Low frequency. What's the answer? Drop the answer in the comment section, my scholar. Are you facing issues answering this ship JAMB must repeat questions? Or are you a last-minute preparation JAMB UTME candidate? Don't worry, don't panic. I will help you. I've been doing this for almost 4 years now. Okay, I've been helping JAMB UTME candidates last-minute preparation. They go still come out, they go perform. People who don't read since 4 months before the exam. So all you have to do, send me a DM to get this what short and simplified lecture notes. And I also have the plan. Okay, last-minute plan for JAMB UTME preparation. Do not miss this opportunity. You can still make a difference in the outcome of your JAMB UTME 2026. I want to see you score high. So send me a DM. My phone number is on my profile. So when you go to my profile or my bio, there you see my phone number. Add up and send me a DM. JAMB 2026 candidate. Today we are looking at the differences between AC and DC. We all know that AC stands for alternating currents. That's a current that changes. It changes itself. It changes on its own. Okay, it changes with the direction given. All right. Then DC is direct current. Okay, it's just a straight current. Straight, another change. It doesn't work change straight up. All right. So we want to understand the difference between both. Okay. AC alternates direction. Okay, it changes direction. All right. While DC steady one-way current. Steady one-way current. All right. So let's look at the difference between peak and root mean square. Okay, or what they call the root mean value. All right. So the peak, which is the peak current, is equal to the maximum current. Okay. So peak current is equal to the what? The maximum current. But root mean square or the root mean value is equal to the effective current. Okay. So the maximum current is different from effective current. Take note. Peak current is equal to what? Maximum current. While the root mean square or the root mean value is equal to what? The effective current. All right. So V, which is what the volt root mean square, is equal to V, which is volt peak over root 2. Okay. So if you want to solve, so just know that V root mean square is equal to V peak over root 2. All right, so easy. Peak current over root 2. That's the voltage of the root mean square or the root mean volt is equal to the peak volt. All right, over what? Over root 2. Very easy. You substitute and you get your answer. Please, 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 please. All these formulas are easy. Put them inside your brain. V root mean square is equal to what? What's the next one? V waiting. Peak current over root 2. And remember that what? Peak current is equal to what? The maximum current. They can tell you the maximum current. They will not bring this as peak current. They will just say maximum. Remember, peak means maximum. When you say the peak of something, you are talking about the highest level, the highest point. All right. So that's for peak. All right. Then the root mean value or the root mean square, they can bring it as effective volts. Okay. So you should know how to substitute. That's why you have to know the meaning and the differences between both. All right. So no go miss this. No go miss this mark. Very easy. The formula is very easy. All right. So if they ask you what's the volt of the root mean square, okay, or what's the root mean volt, so you are going to apply the peak volt over root 2. All right, that's what you are going to apply to get the answer. And this peak volt might not be brought out or might not be indicated as peak volt in your question. It might be indicated as what? As maximum volt. Okay, or this root mean, okay, might not be the volt might not be indicated as root mean. They can indicate it as what is the effective volt. So you already know that it's root mean. They can also bring root mean volt and ask you to look for the peak volt. What do? You make the peak volt the subject of the formula or the effective volt the subject of the formula, and you solve. Very easy. Very easy. Believe me, it's so easy. All right. Now, what is phase difference? Phase difference is angle shift between current and volt. That angle shift between current and volt is phase difference. As easy as that, easy peasy. RLC circuit. R, which is resists. L, which is delays. C, which is stores. So resist, delays, stores circuit. So how do we identify this kind of circuit? The RLC circuit. Resist, delay, store circuit. How do we figure it? How do we know such circuit? We figure it out by analyzing it with vector. When you analyze the circuit with vectors, you figure out if it's an RLC circuit, which is R stands for resist, L stands for delays, C stands for stores, that stores voltage. Okay, so the effective value of this particular circuit is equal to X equal to blah 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 blah. I don't buy the idea of they put this kind of formula for head. Last, if the two set question come out for them, once in the Y, after many years, they will set only one question come out for inside, only one. All right, so Z is equal to what? Root R squared resistance squared plus SL minus SC squared. Everything inside here carry square. That's SL will carry square, SC will carry square. That's this one S. Okay, for what? L, which stands for what? Delays. C, which stands for what? Store. Okay, or you can also use this formula, the shorter formula, which is V volt is equal to IZ. Okay, where I is what? Current, Z is what? Inductance. All right. So there is a resonance in the RLC circuit when XL is equal to XC. Resonance frequency, FR, F for frequency, small r for resonance, is equal to 1 over 2 pi root LC. Please put this formula for your head. JAMB, they set this question well. Calculate resonance frequency. Then they set it well. I don't lie you. Resonance frequency is equal to 1 over 2 pi root LC. Very easy. 1 over 2 pi root LC. Resonance frequency. Power factor. Alright? All these things they inside JAMB syllabus. Now, what's in JAMB symbol? No. What is power factor? What is the formula? Cause tangent is equal to resistance over inductance. As simple as that. Chicken out ABCD. Now that we have understood AC and DC, peak current and root mean value, which can also be maximum volts and root mean volts, we have also understood the RLC circuit and resonance, both the resonance frequency and power factor. Let's now take some JAMB must repeat questions to test the knowledge we've acquired so far and also measure our readiness for JAMB 2026. JAMB must repeat question 112. RMS, which is root mean square value of alternating current, is what? A, peak value. B, peak over root 2. C, peak times root 2. D, peak over 2. What's the answer? Drop the answer in the comment section. This question is so easy. As you look me so, now so we did, two of us, we did look the answer for the screen. Question 130. In a purely capacitive circuit, current leads voltage by what? A, 0 degrees. B, 90 degrees. C, 180 degrees. D, 45 degrees. What's the answer? Remember phase difference. Remember what phase difference? What's the answer? Drop the answer in the comment section, my scholars. Question 114. Resonance in LC circuit occurs when A, SL equal to SC. B, XL greater than SC. C, SL lesser than SC. D, arrow equal to what? 0. What's the answer? Drop the answer in the comment section. This is too cheap. Thank you so much for taking this lecture. Are you a last-minute JAMB UTME candidate? Don't panic, I can help you. Do you need this lesson notes as simplified and short as it is, covering the whole JAMB UTME syllabus 2026, leaving no single stone unturned? You can get this file, okay? You can get this file. All you need to do, send me a DM. Do you want the sharp plan for last-minute preparation that UTME candidates have been using for over 4 years now? All you have to do, send me a DM, drop me a DM through my phone number. Go to my profile. On my bio, you are going to see my phone number there. Add up and send me a message, and I will supply you all this material for you to prepare for your JAMB UTME. Trust me, the outcome is going to be what? Flamboyant. The outcome is going to be worthwhile. It's going to be worthwhile. I can still work on you within this short period of time. JAMB 2026 candidates, don't fail for any reason. Even though say now 2 weeks you take prepare, I can still make a difference in your JAMB UTME 2026 score. Peace out.